computer vision until then. I didn't know that that was a thing. Yeah, and I talked to her, and she offered me an RA, and the rest is history.
Funny because all the network stuff that actually used to be a very niche small community within sysadmin and
Please find.
now there's some. Yeah, Richard taught me my first linear systems course. Still there.
Mm.
I know.
Do you guys send papers to ACML? Are you waiting on their battles?
I did not submit, but I have to review, and they have been flooding me with emails. I don't like it.
Yeah.
Are you reviewing it?
I try to reduce chicken review this.
That's a wise choice.
The ICML, then also the language conferences. I can only do all of them intersect. So if I accepted everything, I can be
Yeah.
a lot of papers.
Mm.
I think some people, especially like the vision people, they get between like CDPR, C, and all the more conferences.
Yeah.
ICML used to give 4 reviews, but now they are doing 6. It's just a little bit too much.
Yeah, we in computer vision we give 6 typically. Depends on the experience of the reviewer, but no more than 6 we try. Yeah, but yeah, it's a lot to review. But we get so many submissions.
Yeah, I think the system is a little broken. Something has to change, but I'm not sure what it is. Maybe we need to get a peer review. There was a New York's experiment, right, that showed the peer reviews just completely randomly released.
Yeah.
Are you organizing ICML this year?
No, I'm for ASML, I just am an author. So, and yeah, I wait in the reviewers' responses to our rebuttal, but they haven't acknowledged. So it's different in computer vision, CVPR and SCP. The area chairs really track down the reviewers for them to go and read the rebuttals and at least acknowledge that they have read the rebuttals, and often they don't change their mind, but at least look at them and see they often put the effort, honor that. But for what I have read for the instructions for ICML is not mandatory at all. So it's up to the reviewer if they want to go and read the rebuttals or not. So it's a little discouraging, but
Yeah.
especially if they make a mistake and you want to
The
tell them that.
culture and literature is a little bit off for me. Something is a little off.
Mm.
Too much information. Too much going on. Oh, yeah. Yeah, this is better. It's better, of course, so it's better. Should we ask either Lawson or Chris if we're connected? So this. Okay. Wait. I can show this out. Yes. Some might say yes, I think you can. Oh, yeah.
Yeah.
Set up the room.
It's like, or what, yeah. Here it is, though. So, That's where it's. I'm trying to do this for longer than we all were. You talked to him, what's that? Yeah. I don't, it's not, I just thought of the one, you know, on the stairs. Yeah. But let's look like $600 to us. His door elbows, yeah. So it's like, well, we don't know what it's like. Yeah. We will say especially because like, when you're trying to remember about business or something like, well, and I think the pet, so I walk past it, finger shake those things, it's like your footsteps. And yeah, it's like I can put grab or grab a waterfall. Well, very. I was asked. It's not the best seating layout. Sometimes they want to have this. I mean, when I help little things like clubs, people okay, person.
Good to see you.
Thank you, sir. I know.
Never here.
I'm here.
Right.
Oh, I finished yours. My last one. Very complicated. It's great.
Apart from the.
I mean, the quick first ratio, it's like I like calculate. So that they do what it does.
Thank you for that.
Sure. What difficult
They
problem
deliver
is
that.
correct now.
You
can bring them over else.
Looks like 3 things.
The later you go in the year. You can separate them out.
We have, I think it's explained that the way they.
No, but I knew at least two of the schools he interviewed at, because I was interviewed like 2 days before me, so I thought, it's like if I run into each other at the airport. We didn't, it would have been hilarious. Going to apply for the school. I didn't really have a partner, sorry, I don't appreciate it. But I mean, because he had like, he rather than CS. So like, there's some schools that just did like 4 different sports. That's how you get to 105. I know, I rest of mine. Oh, that's good. You better. A lot of letters and cheap. Yeah, we go. See, I'm in Daniela, Russ. I tried both of them, but like snap with the camera. All have 1,000 letters. Not like big letters, obviously, because like, I like to respond. And they have these other papers, so you guys will be able to like. I'll come back to this. Yeah. Both are, okay, something is like, but don't have to shame.
Okay, everybody, thank you for coming. We're going to start today's AI seminar. Today's speaker is Octavia Camps. She did her undergrad in Uruguay, and then she did her master's and PhD in University of Washington. Afterwards, she's been a professor at Penn State University for a while until in 2006 she moved to Northeastern here as a faculty in electrical and computer engineering department. Yes. Yeah, so she does really good research in robust computer vision, image processing, and machine learning. And today we're gonna hear from her about her excellent talk and what she's been working on these days. So please greet her with a round of applause.
Thank you, Terry. Can you guys hear me? Thank you. I'm honored to be here. I'm really happy to come and give a talk from some of the research that our lab is doing. So the title is in the slide is Frugal, Interpretable, Dynamic Inspired Architectures for Sequence Analysis. As a bit of my background, I did my master's in control theory. So I know enough control to be dangerous. And I like to apply a little bit of that in computer vision. So this work is funded in part by NSF, ONR, and DHS. And of course, the slides are not moving. There. All right. This work cannot be possible without the work of a lot of students and postdocs and my colleague Mario Snyder. So, all right. So the talk I have organized it in these 5 portions, and depending on time, I might not get to the 5th item over there. That's okay. So I'll start talking about the motivation, why I'm working on this area, and then I will give some background on dynamic systems representations. I know a lot of people here works in robotics, so controls for you is not foreign. I'm used to computer vision audiences, and I have to kind of give a baby tutorial about that. So if you get bored with it, please mind. I don't mind. I think I will get to interesting things. Hopefully, the way we use those things will be interesting. If, on the other hand, you are not exposed to these ideas before and you have questions, feel free to interrupt me anytime. Okay. Then I will show how we can use those ideas into designing architectures for analysis of temporal sequences. And then I will give a concrete example where by using this type of approach, we were able to actually significantly improve the performance of a neural network that was doing cross-view action recognition just by using the insights of our design. And then if I have time, I will talk about how to extend this to nonlinear systems using Kuhlmann operators. All right, so why sequences? Okay. I think everybody agrees with me that the world is dynamic, things are moving, things are changing. So we are exposed to temporal sequences all around us all the time. And of course, I'm a dog person, so I had to show a puppy video over there. One of them is my puppy, actually. We have sequences. So if we want to understand the world, we need to understand how sequences are. Also, we know that, these experiments are very famous, is that by looking at the temporal coherence of the data, that has very important cues of what we are observing. So if we play these videos, we can see patterns, right? On the right-hand side, we see 2 people walking to each other, greeting, hugging, and so forth. On the other ones, we see constellations of points that they do move together. So our eyes, our brains are used to integrate that temporal coherence and making sense of that with very little actually data. And also the world is causal, right? By looking at the past, we're able to predict the future and make decisions that could be critical to our life. For example, crossing a street, we know when it's safe, when we have time before a car will run over us. So knowing that causality, we can use that again to do inference of the future and making decisions. So using this temporal coherence, causality, then we can try to do, obviously, inference with sequences, for example, predict the future, doing data imputation, filling the blanks, did the green trajectory continue in the yellow one or turn around to the red or continue to the blue? Can we do inference about that? And also we can also detect anomalies in a temporal wise way, okay? And of course, we can also do classification, okay? For example, we can try to classify activities of humans by looking at the way they're moved. And there is a very rich literature that deals with sequences now in machine learning and computer vision. They typically involve some kind of either recursive neural network or transformers more lately, okay, that do process sequences and are quite successful. There is no argument about that. However, I think you have to agree with me that most of these models are black boxes in the sense that they have millions of parameters, and sometimes it's really hard to understand what these parameters are doing or learning or what's the effects. And so they are not physically interpretable. So in our lab, we are looking for developing models from data, like these other ones I just mentioned, but at the same time, we want them to be explainable, interpretable, so that they follow physics and that they're rich enough to capture dynamics that are relevant to understanding the world around ourselves, but also simple enough so they are fast to train and doing inferencing. And we want them to be frugal, to have as few parameters as possible. So in a sense, what I'm looking for is getting these black boxes and putting windows on them so we can look inside what they're doing, and also providing some knobs and handles that we can turn things around so we can affect the performance or what the output of those networks are. Okay, so let me talk again. As I mentioned, I'm going to do a baby tutorial on dynamic vector representation, so we are all in the same level field when we start using them. And so really, here is my first starting point, which is that we're going to use as input sequential data. Okay, and by this I mean uniformly ordered sample data. Okay, there could be missing points, but in principle, it is evenly spaced, and there is an underlying order. And this could be point trajectories, or it could be dynamic texture, or anything, again, that has this property. Okay. All right, so, and also going to be working in the discrete domain. So really, my measurements are a sequence of discrete measurements, okay, like these white dots, and y sub k means the measurement at time k. Now, these dots are kind of a pain to draw and do it, and they are actually sample of an underlying continuous system. So in the rest of the slides, I'm going to just do this red wiggle to signify, but keep in mind that I'm working with discrete data, okay? All right, so what we're going to be doing is we're going to model this data, okay? And the first model that we can think of is a linear time invariant system that has produced the data, okay? And as George Box says, all models are wrong. Clearly, there are a lot of temporal sequences out there that they do not come from a linear system, but sometimes it's surprisingly useful to use a simple linear time invariant system, okay? Now, if this is too simple for you, we can, for example, have multiple LTI systems and switch between them. And that turns out actually they are universal approximators, so you really can approximate. The problem, of course, is how many LTI systems you need and how they switch and so forth. Okay. Another possibility what you can do is put nonlinearities at the beginning, at the end, the front and the end, so you can have, some mapping from the data where it lives to a place where now the dynamics are linear, and then you go back. And this is basically the principle that's using incumbent operators, okay? And the last example that I have in my talks is about that, okay? And of course, in these days, the nonlinearities typically are implemented using neural networks, okay? And of course, you can combine both, right? You can have switch linear systems and nonlinearities if you want to have a really complicated thing. All right, so as you saw on all these representations, the building block or the core was an LTI system, okay? So I'm going to focus in the next slides on this very simple model, all right? So I have a box there that is excited by an input. It might be an impulse or something else. And I am serving y sub k as the output, okay? And I want to represent this. So one way is represented just by the data. I keep the samples. And in fact, it turns out that taking the samples and rearranging them in a Hankel matrix where we have a sliding window of the data and arrange them in columns with a stride of 1 carries a nice information. The rank of this matrix is important. The null vector, as we're going to see, is important. So that's one way of doing it. So it's basically model-free. It's just based on the data. Okay. But of course, we can have the transfer function, or we can have a state space representation, or we can have an autoregressive model. Okay, now here on the bottom ones, I didn't have an input. On the top ones, I do have an input. It's very easy to add inputs to the bottom ones. Just I'm oversimplifying here. Okay, now all of these are alternative representations of the same system. They're equivalent. They all carry the same information. Okay, you choose one or the other depending on, well, the one that you like the better, that makes more sense for a particular problem. Sometimes it's easier to have an intuition of what they're representing. Okay. I believe that they bring interpretability and we can understand things. And some of them are more obvious than others, depending on the representation that you use. So for example, if I look at the transfer function, what I see is that, well, my system is really the superposition of n systems, each one corresponding to the poles. And actually, that n is a little fishy in the sense that the poles could be real or complex. If I'm complex, then I need the conjugate pairs, and so it will be second-order systems. If I have a real pole, it will be a first-order system. But what it says is that this system is a linear superposition of n first- and second-order systems. Okay? And moreover, we can look at these systems by looking at where the poles are located in the complex plane, and we know how they behave. So these become dynamic atoms that can use to be representing and interpreting my data. Okay, so that gives interpretability that way. Of course, the more poles I need, the more complex the dynamic is going to be. Okay, if we look at the autoregressive model, then it's pretty obvious what this equation is saying is that to predict the measurement observation at time k, I will use a linear combination of the previous m measurements. That means it's the memory that I need to actually make a prediction. So for example, if I'm moving with constant velocity, I need 2 measurements to be able to compute basically the velocity and predict. If I have constant acceleration, I need 3 measurements to be able to estimate the acceleration. So this is telling me a measurement of the complexity of the system, what the memory I need to have to represent the sequence of the data. Okay. Another thing is that we can take the Z-transform of this equation and we get the characteristic polynomial of the system. And that polynomial, the roots are the poles of the system. Okay, so again, this ties back with the transfer function representations. Again, they are all equivalent. They all have the same information. Some of them, it's more obvious by looking at equations, and others you have to dig a little more. Okay, all right, so the roots of that characteristic polynomial that has the same coefficients to the autoregressive model are the poles of the system. The Hankel matrix, again, is a rearrangement of the data on these diagonal patterns. Okay, in the absence of noise, we know that this matrix has to have rank n, again, which is the memory of the system. So you collect your data, you estimate the rank. Of course, it's going to be noisy, so it's going to be full rank. You have to make a decision, you know, what is the actual rank of that matrix, but that tells you how complex that system is. Is it constant velocity, is constant acceleration, is something else? Also, if you take the elements, the coefficients of the characteristic polynomial, that vector is a null vector of the Hankel matrix. So again, all these representations are all tied together. In the state of representation, this representation is not unique, right? We can change the matrix A, B, and C and still have the same model. But we know, first of all, the matrix A is n by n, where n is the memory of the system. Again, that's the state of the size of the state. And the eigenvalues of that matrix are the poles of the system. So again, everything is related. Okay, so I claim that these representations, except maybe for the Hankel matrix, which is basically just the data, they're frugal, meaning that I only need a few parameters to describe the systems, right? So I need the complexity and the number of poles I have. The poles may be the coefficients or the matrix A, B, and C, or the coefficients of the autoregressive model. Okay, but once I have this, I have the blue box, right? I can generate as much data as I want from that blue box. Okay, so once I have that, then what it allows me to do is data inference, like again, prediction, imputation, and classification, and so forth. Okay. All right, so now that we are all on the same page, okay, let's see how we can use these representations or as an inspiration to design architectures that can process sequential data. So I'm going to be talking about here a video that has a human performing an action, and really what I have is a skeleton of that person. And that's just an example, but it could be any type of temporal trajectory. That's my input. And moreover, it can be many trajectories at the same time. So here I have all the trajectories of all the joints of the human as being as an input of my architecture. Okay, so here Y is a matrix that has T rows, T meaning the input, the number of samples of my sequence that I'm using, and 2J over here because I'm assuming it's a 2D skeleton, okay, and I have J joints. So each coordinate has 2 coordinates, X and Y. Each joint has 2 coordinates. So that's my input sequence. Okay. Now let's assume for a minute that I do have these atoms I mentioned earlier when I described the representation using a transfer function, where I have the responses of simple systems, first order and second order systems. Okay, suppose I have that. Okay, so with these atoms, what I would do is I'm going to create this matrix, which is a dictionary, where row-wise, I'm advancing on time, and column-wise is one for each of these atoms. Okay, and what these columns are the impulse response of these systems. Okay. And now what I'm going to do is, and as you say, this dictionary, I want it to be wide, okay? I want to have a lot more atoms than the temporal number of samples that I have. All right, so now with this, what I'm going to do is design an encoder that is just an optimization layer that will find a sparse decomposition of my input data using this structured dictionary, okay? Look at this dictionary. The columns have a very structured pattern, right? Each column has 1 pi power I, pi power I plus 1, and so forth. So if I know the pulse of the system, I can write this matrix as big as I want, you know, as many rows as I want. Okay, so I'm going to try to optimize this. Why I'm going to do that? That's what my encoder does. Well, the first term is implicitly assuming that my data has Gaussian noise, and I'm trying to find the best decomposition between the input data and the dictionary I have, right? So if I didn't have noise, it would be exact. If I have noise, I could do, for example, a least square, and I will get a solution, okay? So this is saying, you know, I have a good match between my data and my dictionary. The second term is a regularization term, which is doing is, well, I want my dynamics to be as simple as possible. I don't want to use all my atoms. I want to use as few atoms as possible. So I have a sparsity constraint that I would like to have an L0, but it's easier to deal with an L1, okay? And this optimization problem can be solved using off-the-shelf algorithms like FISTA, for example. Or it can be actually implemented with a neural network as well, with using FISTA, for example. Okay? We use FISTA. So it's just an optimization layer. So there's no learning parameter so far. Okay. All right. So once I do that, I have these features over here, right? So this is my encoder. These are my sequences. And these features here, what it's representing is that they are sparse. So the blacks are zeros, and I only have a few non-zero elements for each of my trajectories. Okay. Now that I have the encoding part, I need the decoder. The decoder is just a multiplication matrix. What I do have is that dictionary, which I can actually add rows to it as much as I want because I know the structure. Okay, so it doesn't have to have the same number of rows as my input data. So that means I can predict the future. Sorry. Okay, and so I multiply my latent variables with extended dictionary. Oops, sorry. Here, where I have these extra rows, and that will give me y hat, which is a reconstruction of my input data plus extra frames. How many? Well, up to how many rows I have added over here. All right. So where is the learning? Well, the learning what's happened is that I told you I have a dictionary, but the truth is I don't know what my dictionary should be. Okay, so what we're going to do is we're going to learn where to place the poles in the complex plane by doing gradient descent, right, back forward in the network by comparing my input against my reconstruction. So it's just an autoencoder, okay? So self-supervised, right? And what I'm showing here in this GIF on the bottom right is how the poles, we start them by doing a random distribution on the complex plane near the unit circle, and we train it with sequences of humans doing actions, and these poles are going to start moving, okay, towards where I want them to be. Yes?
Is D being trained together with the encoder?
So C is the output of the encoder, okay? So the encoder is just an optimization. Okay, the encoding is doing the optimization. So if D is given, so at the current state, you initialize your dictionary. This encoder over here, solve FISTA. That gives C. With C, you multiply by the extended D. That gives you Y hat. Now you compare Y hat against Y using your favorite loss, for example, L2 loss. Okay, and you can do it only in the reconstruction or reconstruction and prediction. All right, and that propagates, and what's going to do is you move the poles in the dictionary. Okay, so the number of parameters that this network is learning is just the number of parameters I need to describe the poles in the dictionary. Each pole has a magnitude and a phase, so 2 parameters, and I know they have to come in conjugate pairs, right? So if I have a real system in the world, if I have a complex pole, I do have to have the conjugate, okay? So only 100 parameters really, and I can do that, okay? So the properties of this architecture are, first of all, is end-to-end self-supervised trainable. I don't need any annotations, it's just an autoencoder paradigm. It is frugal because it has very few learnable parameters, only the parameters of the poles in the dictionary. It is interpretable because those poles are the poles of the system and tell me a lot of what is going on in the dynamics. I can use it to encode sets of sequences in one shot. I can have the Y matrix and just pass it through, and I can predict multiple future frames in one shot as well, because that just says a matrix multiplication. Okay, it makes available all the LTI tools that are out there that people that are much more proficient in control knows and can teach me how to use. For example, I can use Kalman filtering in the middle, right? Limitation, yes, assumes the dynamics are linear. That's a restrictive limitation. But I told you that we can actually incorporate switching, for example, by seeing whether the prediction of the system is far away from the actual measurement, and we can decide on switching there. We can do Kalman to decide what is enough of a change. We can also add nonlinear mappings in the front, okay, and in the back. And so it can be generalized to more complex things, as I'm going to show in the last example. Okay, so let me show you a benefit of designing this type of architectures, of having the insight of what the architecture is doing, what is the latent variable meaning of things, okay? And so I'm going to put this in context on the problem of cross-view action recognition. And for those of you that don't know what this problem is that we want to recognize actions, but during training time, we have access only to a limited set of points of view. And then at testing time, we're going to try to recognize the action from a novel, unseen viewpoint before, okay? And the reason we are interested in this problem is very practical. We have this project funded by DHS for airport security, and this is actually a mock-up of a security that we have built at Northeastern, where the task is to associate the items in the bins that you put in the conveyor belt before going to the gates with the passengers, so you know what belongs to whom. Okay, and so that involves doing action recognition, recognizing that you're putting something in the bin or removing something out of the bin. Okay, and we want this to work in any airport, right? And so we want to be able to train in one airport and then test it in a different airport. And the viewpoints can be very different. Okay, so we want to be able to have to do the least fine tuning and data collection whenever we change venue. Okay, so it has really a real application besides being, a computer vision problem that people have been publishing on. Okay, so we started as a baseline. Let's take this encoder decoder that I mentioned earlier, and just take my RGB frames, and inspired by the dots experiment, let's take an off-the-shelf software that computes skeleton of the person in the video. OpenPose is great. And so that's the second frame here. Okay? Then pass the trajectories of the joins to my pre-trained encoder, right, that has a dictionary with it. I get these latent features that are the coefficients of the poles and use these features to classify. And then spit out a label. And we try, for example, in the UCLA dataset that has 10 actions, 10 actors, 3 different viewpoints. You train with view 1 and view 2, and you test with view 3. Okay, and we tested, and we got the score for the cross view setup, 87.5%. Okay, is this good? I don't know. Let's look at the state of the art. Okay, so back in 2020, the best algorithm out there had 83.1%, so we are better than them. More recently, last year, Shah et al. Produced in Rugby this other paper that has 91.7, which is bigger than it. Yes?
How many classes are there?
So there are 10 actions. So the classes is the number of actions. Yes. Okay. All right. So we are sort of in the middle, right? We're not at the top, but keep in mind that these two papers I'm mentioning here, they use 4 RGB. I'm using only the skeleton. And second, they are actually solving the cross-view problem. So they address the problem that you train with one viewpoint and you're testing with a different one. And they did it in different ways. The first paper does render intermediate views. The second paper uses contrastive learning to try to learn some kind of invariance. We didn't do anything like that. It's just the vanilla dynamics. Okay. All right. So let's see. Can we do better? And that's where, again, the insight of the design of the architecture can help. Okay, so we look at the same action from 2 different viewpoints. And I'm looking in green here, the trajectory of one of the hands of the person doing the action. We can see that that curve, as looking at samples, they look quite different from view 1 and view 2. Okay, and so that means that a classifier has a hard time classifying things just based on the sequences, because if I'm changing the viewpoint, I train in view 1 and then testing in view 2, it has a difficulty there. Okay. So let's look at the architecture I'm using and see, okay, I know that the trajectories are not invariant to viewpoints, that they do change. How about the C features? Are they invariant? Okay. But it turns out it's very easy to check that they are not invariant. Okay, so remember C, like the latent features, are such that when I multiply with a dictionary, I should get back the input. Now, if I do a scalar rotation of my data, I multiply by the matrix in front, right? In general, that matrix times D is not going to be equal to D. Okay, so the coefficients have to change. Okay, so these features are not viewpoint invariant, depend on the view. Okay, and so if I train with one view, the classifier will have a hard time in the testing. All right, so can we do better? Okay, so let me talk about invariance. Right, so I'm very old, sorry. I started computer vision when many of you were in elementary school, or maybe not born. So when I started in computer vision, we spent a lot of time talking about invariant features, okay? And we all sort of know what we meant. We meant that we want to be able to recognize an object, even if it changed the view, the insides. For example, those really pretty sunflowers, the ones on the front are much bigger than the one on the back, they're still sunflowers. And the dog is still a dog, even if it's upside down. There's something intrinsically that has not changed when we do things, or we change the illumination. Okay, and so people went back then to geometry. And I don't know how many of you can recognize the names or the faces in this picture, but this is from the early 90s. Many of them are the authors of your textbooks in computer vision. Okay, and so a lot of people spend very smart people spend a lot of time working in geometry and trying to derive things that you could go and measure in your images that did not change when you change the camera viewpoint. Okay, that was the idea of invariance. And then we have, for example, C features, right, that they try to do the histogram of the gradients of the edges, again, trying to achieve some kind of invariance. Then 2011, 2012, AlexNet happens. And we all have the success of deep learning. And what happens then is that now invariance is learned just by throwing more data to your network, okay? So if you assume that ImageNet has views of cats from any viewpoint, then the network is going to learn to recognize a cat no matter what position it is. And if you don't have enough data, well, you create it, you do data augmentation, okay? And that's what actually contrastive learning is doing, okay? All right, so I want to be more in the field here on the top, where we use principles rather than just throwing more data. Okay? Now, invariance in the time domain is not so well understood. What does it mean to have invariance in the time domain? Okay, so again, what we want is something that is intrinsically not changing, no matter which viewpoint we're looking things from. And what is not changing is the actual physical system that's doing the motion. It's the same person no matter where I'm looking it from, okay? And it's doing the same action. It's walking or bending down or sitting. So there's something invariant there, right? It's the blue box that's creating the data and somehow, okay? So that's the insight, okay? So when we look at sequences and we want to do inference and classification, again, there are two changes that I'm worried about. The first one is very obvious, is that if I change the viewpoints, I said these sequences are quite different. So can we get something that still does not change when I change the viewpoint? And the answer comes by, for example, looking at the autoregressive model representation, okay? So let's say I have here, the y2k, let's say are the 3D coordinates of the joint over time, okay? And now what we're going to do is I'm going to image that motion in 3D from different 2D views, okay? And so to do that, we do less be a simplification. Instead of doing a perspective projection, let's do an affine projection. So it's basically a rotation and a scaling, a similarity. Okay, so now I can't have by projections, which is just applying a matrix to y. And now because all of things is linear, that's the beauty of using linear time invariant systems, the pi matrix can go inside the sum of the regressive model. And then what we see is that the modified coordinates have the same regressive model coefficients. Okay, so the coefficients themselves are the same and the number of coefficients is the same. So the complexity of the dynamic has not changed. And actually the coefficients to compute that prediction remain the same, even if I have changed the viewpoint. So we say that the coefficients of the regressive model are invariant to linear transformations. Okay, so to view change, just if I'm using the affine simplification. Okay, I'm using affine coordinate to have to do that, and I had to have an extra one. Okay, so there's another change that I am worried to, which is different initial conditions. I have two cameras, sorry, Italian descent. We have two cameras looking at the sequence, but they are not necessarily synchronous, okay? And so one of the cameras might have started looking at the action when the action has already started and been observed by the other. So it's not that the first frame here corresponds to the first frame here. In this case, it's actually the second frame here that corresponds to the first frame here. So can I have invariance to when I starting observing the sequences? And the answer is yes. And to do that, I'm going to use the Hankel matrix representation and the fact that the coefficients of the autoregressive model are in the null vector of the Hankel matrix. Okay. So let's see how I show it in a second. So let's have now the state representation where I have no inputs. I'm going to assume I have an initial condition without inputs. And now what I'm going to do is I'm going to propagate that initial condition x0 through these dynamics equations, right, to get up to yk, right? So I take xk minus 1 times a times c, or c times a squared, xk minus 2, and so forth, or c ak x0. Why do that? Well, because if you remember, the Hankel matrix over here has in a diagonal pattern yk minus 1, yk minus 2. And so that means that using these equations, I can factor the Hankel matrix into the product of these two matrices. The matrix on the left, the matrix on the left is a well-known matrix for those who do control, which is called the observability matrix, and does not depend on the initial condition. It depends on the dynamics of the system, but not the initial condition. The second matrix is the trajectory of the state. That depends on the initial condition, okay? But why is this useful is because I know that I have this vector here, omega, I'm going to call it, that is the null vector of H. That is omega times H is equal to 0, which means that omega times this matrix has to be equal to 0. And again, these matrices that don't depend on the initial condition. So that means that the null vector is independent of the initial conditions. It's invariant to the initial conditions. Okay? So the coefficients of the autoregressive model, because remember this vector is nothing more than that, are invariant now to the initial conditions as well. So they're invariant to the viewpoint on a fine transformation, and they're invariant to initial conditions. Okay. One more step, okay? So now that I have these null vectors invariant to both things, well, remember that these coefficients that form the null vector are also the coefficients of my characteristic polynomial, which means the characteristic polynomial is invariant. And that means that the roots of that polynomial are also invariant. And remember, the roots are the poles of the system. Okay, it took me a while to get there, but what I'm trying to show is that the poles of the system are invariant to both viewpoint changes and initial conditions. Okay, all right, so we know that C, my features here, are not invariant, okay? But what I shall show is that actually the locations where I have these colorful dots, those are invariant because the location in that array over here is telling which pole I'm using in the dictionary. And that doesn't change when I change the viewpoint. It does change the coefficient. How much of each pole I use, it changes. But the fact that I'm using pole number 5 does not change when I change the viewpoint or when I change the initial condition. Okay, and that's again, I could do that only because I know what this means. I know that I'm, building a system dynamics representation here. Okay, so the solution, yes.
So just to make sure I understand, if you had the camera from the other side, you still will get the invariance?
So it's very good. So the question, there's an unsaid assumption here, which I'm saying that the system is observable, which means that I can estimate the dynamics of the things from the observations I have, okay? That I can estimate the state or the initial trajectory. If I'm not seeing the front and you're walking like this, I will never be able to generate that because I have never seen it. Yes.
But if you get the skeleton, then you're good, doesn't matter which direction.
Yeah, it doesn't matter, yes, yes. And the good thing also is that if I have occlusions or missing data, the network is able to actually cover that because using the structure, again, the temporal coherence, it can impede the data that's missing. Okay. So the solution to improve the performance, it was very simple. I took the architecture I had before, but now, before going to the classifier, maybe the classifier, with enough training data, we have learned this, but I don't know. It was much easier to tell the classifier, let's do thresholding of this. If something is not 0, let's make it just a 1. So create this binary array now that says this pole is being used, this pole is not being used, and use that as my features for the classifier. And the result is that we got 96.6% performance, okay? Just by adding that module, and we knew exactly where to add it and how to add it because we understood what the architecture was doing. Okay. The other papers use also RGB, so why not? Let's have an extra branch that's basically an I3D, and there's nothing really novel here, but uses the context around the skeleton, and with that, when you add that, we go all the way to 99.4%. Okay. The other thing is that this is really agnostic to the type of data. We did it with 2D skeletons, but it works the same with 3D skeletons. And so we went and used the 3D data and checked there, and we achieved 99.9%. So basically, we saturated the data set. These are the current state of the art. Right now. Okay. Here are more. We use all the other data sets that you need to publish papers in the computer vision conference. Yes.
Why does 3D seem to be like easier than 2D?
Oh, that's a very good question. So when we started and we look at that, the first thing we noticed was that, and I think it's easier to kind of align your data in 3D, and the systems have a better way of really aligning those things. Okay, yeah. The other thing is a small detail is that when we are doing this, we are very naive. And so the architecture is not enforcing any type of, in principle, any interaction between the different sequences. They're all processed together. If you actually do add coherence in terms of the joins, you can boost the performance even further. Yes?
I actually had a sort of similar but a naive, outside of a computer vision standpoint question on that. Can we, like, I imagine like a point in 3D space with like 6 degrees of freedom, then projected onto a plane. Do we lose information in that case? Like, can this 2D representation of 3D skeleton capture the full three-dimensional movement of a human? Or I'm wondering if that's maybe part of this difference.
It depends how rich the motion is. Okay, so and before deep learning, in another life, we had a paper on the structure from motion for perspective views. Okay, and there, up to then, people basically you did reconstruction up to a perspective transformation, because unless you added extra information in terms of angles or size, it was an ill-posed problem. Using dynamics, we actually can enforce that, and actually we recover only up to a scaling factor. So we remove the perspective distortion, but you have to really excite the modes, right? So you have to make it that the system is observable, that you have to have enough observation from different views so you can actually do that. Yeah. But the way the thing will deform in 2D will give you the information that you need to do that. All right. Okay. So actually, I have time for the last example. Okay. So up to now, the example I gave you used the simplest of all the models. It was a single LTI system describing each sequence. Okay. The complexity was given by the number of poles being used in the dictionary, and each sequence can choose different poles, right? But each trajectory was one dynamic system and linear and time invariant. Okay, so here what we're going to do is borrow a page from Kuhlmann theory and actually put also nonlinearities, okay? And this is work that was presented in the last L4DC with Armand Gomez and my students. And here what the task is, this is a little more theoretical paper, so the examples are more toy. What we want to do is disentangle the objects in a video and not only give the descriptions of their elements, but also the dynamics. So in self-supervised video decomposition, normally people would take a video like this. This is the moving MNIST, and it will decompose in terms of the objects, how many objects are here. So here are 2, and number 3 and number 1. What are the positions? So we'll give the coordinates of the center of the object, for example, an appearance description of what, the pixel gray level values, the size, whether the digit is visible or is occluded, and so forth. But then for the dynamics, it will be more like, well, it moves this way, and it will be represented by a kind of LSTM or RNN, but really no decomposition or understanding of what that motion is. Okay. So what we want to do is to give physical meaning and interpretability and manipulability also to not only the appearance, but also the dynamics. Okay. And so we are going to basically replace the nonlinear recursive neural network by using a Kuhlmann setup where we take the data that we assume it has nonlinear dynamics, we project it into a manifold using a neural network, and in that manifold, we assume that the dynamics are linear, then we use our magic there, and then we decode back to the original. Okay. All right, and so it's data-driven totally, okay, and it's an alternative to basically recursive neural network, but allows us to inject in the middle a linear operator. And by the way, we are not the first one doing this. This Kuhlmann operator neural networks exists for a long time, but what we're showing is how you can actually use that to manipulate and do things with the data. Okay, so the interpretability again comes because that linear operator in the middle, right, it's going to advance things using linear dynamics, okay, and as I have shown this picture before, the eigenvalue, the composition of the operator, the eigenvalues of the dynamic matrix corresponds to these dynamic atoms, and we can really understand what they are doing. Okay, so this is a overview of the architecture. So basically, we have as input a set of frames with moving, moving objects. We use off-the-shelf tracking. Use your favorite one. We were using one that was based on attention, and so we have a tracker for each object. And we have a maximum number of objects. We don't know to need no a priori how many objects, but we have a maximum of them. And then to each of these objects that have been tracked, we associate a set of latent variables that we give them physical meaning of what those variables are going to represent. So we have a variable that says whether it's in the top layer or is behind something. So it has the visibility. We have variables that represent the shape. A confidence, whether we see it or not, depending on the tracker, the position and the scaling, and also the appearance of the pixels. And this we're going to actually model stochastically. And then what we do is we take these post coordinates and we have them in temporal sequence. We gather, say, the last t measurements of those. And that is that we must do the nonlinear mapping where now we have the Kuhlmann operator. Okay. So this is an example of the experiments. For the sake of time, I'm only showing this one with a crop circular motion. Again, this is the moving MNIST, so the digits are moving in kind of circular pattern. But what we have done is artificially crop the top part of the frames, so there is partial occlusion. And so the first row here is the ground truth of the video and of the predictions ones, right? And then on the bottom, the next ones are reconstructions where we have competing approaches, and our approach here is OKID. Now, what I want to point out with this experiment is that when we look at the eigenvalues of the Kuhlmann operator, what we see is that, first of all, there were a bunch of small eigenvalues that they can be actually removed, and the performance remains similar. So we can do, system reduction very simple. And then what we do is we take some of the eigenvalues and we manipulate them and look at what is the effect in the reconstruction on the predictions of the video. Okay, and so this last rows over here, what I'm showing is that we take this pair of eigenvalues that are on the unit circle, and we do two different modifications. One is we move it in and out of the unit circle. So we change the magnitude of the pole, or we keep it on the unit circle and we change the phase of the pole. Okay, and so what we're seeing here is when we, for example, we increase the magnitude to 1.5, the trajectory of the number 4, and we can do this for any object. So here we're manipulating the object number 4. What we see is that the trajectory saturates because we are going above 1. And the same thing with the phase. What we can see is that by playing with the angle, we can change the frequency of the trajectory of the number. So again, what this allows is those knobs that I was thinking. So the previous example shows I have a window and I could debug and add a module. Here, because I have interpretation, I can actually play and edit the outputs. And it does recover, actually, I should point out, very well the portion that has been occluded. Here's another example. This is with a double pendulum. This is the video. This is the input, and this is the output prediction. So it does quite well. So the last trick, which I think is really cool, is that because I have this Kuhlmann operator, that it's pushing in time the latent variables, what I can do is, for example, temporal super resolution. Okay, because what I can do is, instead of using the Kuhlmann operator K, I can do K 1/2 or K 1/3 and interpolate frames in between. And I can also do K inverse and do actually propagation in the past rather than in the future. And this all came for free, just because I know what this matrix is doing. All right, so what are the take-home messages? I believe dynamic-based representations are a good thing to have in your toolbox. Okay, they're compact, they're easy to train, they're easy to incorporate in more complicated networks because they're end-to-end trainable, so you can put them as a module in your favorite architecture. They provide interpretability, explainability, the editing capabilities. I think they're really cool. It also allows us to have invariant features by design. I don't need to give 1,000 examples of augmented data to get that insight. I know that these features had to be invariant, and I can use that. That simplifies the model, so I have a lot less number of parameters to be learned. The network trains much faster because of that. Needs less data also as well. Okay, and as I saw, this modality agnostic, really what it is good tracking, okay? If you give me correspondences over time, you can throw it into this architecture. So with that, thank you. Yes.
I would like, thank you for that great talk, by the way. I have a question tying back to the tracking that you mentioned at the end. Can you look back the insights that you have from control theory to improve tracking so that the tracker will take advantage of all this?
Sure, yeah.
Dynamics?
Yes, definitely. So we have done in the past, before deep learning, we had to do tracking using the Hankel matrix, for example, and and it worked much better than, say, particle filters or Kalman filtering, just by enforcing the dynamics. And the idea was, in that case, that it was model free, meaning I didn't have to make the assumption that it is constant acceleration or constant velocity. The data will tell me. And so definitely, again, yes, you can put this in a tracker, and you can use your favorite filtering in the middle as well to improve the tracker. So you can do, for example, Kalman filtering and such. So definitely, yes.
In all examples, there were relatively sort of notion of objectness in the examples. So you're kind of tracking Lagrangian sort of particles moving around. What happens if there are no such like objectness, like if you had a video of waves or?
Yes, so I didn't put example because I thought I was going to run out of time, but we have actually done apply this architecture to do video prediction on frames, where we took the way we did it is we predicted. We learned the dynamics and predicted the optical flow of the pixels. And once we have that prediction, we can map the points. Now, what the problem that this approach had, and we didn't pursue further, students sort of graduated and left, but it is that as things get unoccluded and disoccluded, you have to do something more than that, right? Because this cannot do magic. Like he was saying, if you don't see the front of the person, I cannot predict what I never have seen or have a clue of it. Because it's really based on the motion. It's not using any pre-knowledge about how a person looks like or how a house looks like or so forth. So it needs to be married with something else. Okay, so just in itself is not enough. You need more stuff. But yes, we have done it with dynamic textures, and we have done it as long as we don't have significant occlusions, and the occlusions, it works nicely. We did it with traffic scenes, for example.
So the implementation question, I'm curious on the numbers example, if any like addition to loss, was it all added to sort of ensure stability to the unit circle? Like I've heard of some work looking at doing that recently.
Okay, so it's even with the human activity, right? We put some safety boundary. We know that poles that go really high, will become unstable. They're not useful. Same thing, poles that go very close to zero. We don't want them either, especially if you have long horizons, right? So if you're looking at long horizons, you have power to the time step, and so very quickly blood. So we put, we try to chop it. In general, we don't need to do a lot of that because we are learning from real data, and real data typically doesn't have that behavior. But yes, a lot of debugging hours had gone on that part of the project. Thank you. You're welcome.